All right, so we all use the internet literally every day. And let's be honest, most of the time, it just feels like magic. But it's not. It's actually this incredible feat of engineering. So today, we're going to pull back the curtain and demystify one of the most common things we do, but probably understand the least: what actually happens to your data every single time you click a link.
So you click on a link, let's say to Cisco.com, and bam, the page just loads. It feels instantaneous, right? But in that tiny fraction of a second, a request from your computer has to travel, it could be across town, or it could be halfway around the world, navigating this insanely complex web of devices just to grab that page. The big question is, how on earth does it know where to go?
Well, the journey always starts with the question. Before your computer can send anything, it basically has to ask for directions. It shouts out, "Hey, where is www.cisco.com?" And it sends that question to something called a DNS server, the domain name system. The easiest way to think about DNS, it's literally the internet's phone book. It looks up that human-friendly name, cisco.com, and finds the computer-friendly number it's tied to, the IP address. Once it has that address, now the request is ready to actually be sent out.
Okay, so our little request now has a destination address, but it's not ready for the trip just yet. It has to get dressed properly. You can't just send it out onto the internet, naked. It needs a few specific digital layers to make sure it gets there safely.
And this process has a name. It's called encapsulation. Just imagine you're mailing a really important letter. First, you put it in an envelope, right? But maybe for a super complex delivery, you'd put that envelope inside a bigger one, and then maybe even that one into a special courier pouch. That's exactly what your computer does with your data. It wraps it in several digital layers, and each one of those layers has a very specific job to do.
So let's break down how this actually works. The very first wrapper is called the TCP header. This creates what we call a segment. Think of this like adding certified mail tracking to your letter. It's what makes sure all the pieces of your data arrive and that they arrive in the right order. Super important. Then, that whole segment gets wrapped in an IP header, and that creates the packet. This is the main address for the entire journey. It has your IP address and the final destination's IP address. And finally, for the last layer, you've got the Ethernet frame. This is basically like a little sticky note just for the local mailroom. It doesn't care about the final destination, it only tells the network which exact device to hand a packet to next. And with that, our data is all dressed up and ready to go.
All right, our fully dressed packet is ready. But now it has to find its way out of your house or your office. Before it can even think about hitting that global internet highway, it has to navigate the local neighborhood streets first.
And to get around on these local streets, the packet actually relies on a totally different kind of address. So we've talked about the IP address, right? That's like the global street address for a whole building. But if you want to find a specific person inside that building, you need their name. And that's exactly what a MAC address is. It's a unique, permanent hardware ID for every single network device. So on your local network, all the devices use these MAC addresses to talk directly to each other.
So who manages all this local chatter? That's the job of the switch. You can think of it as the traffic cop for your local network, or maybe the mailroom manager for your office building. It knows the MAC address of every single device plugged into it. So when our packet leaves your computer, the switch takes a look at that local destination, the MAC address of your internet gateway, and it sends the packet directly there. It doesn't just blast it out to everyone else in the building. It's smart. It's the traffic cop, making sure everything goes exactly where it needs to.
Okay, so our little packet has made it across the local network. It's successfully navigated the office, so to speak. And now it arrives at arguably the single most important device in its entire journey, the gateway. This is the device that connects its small local street to the massive global internet.
Yeah, and this quote here really gets to the heart of a crucial handoff. What it's saying is that the local network, with all its switches and MAC addresses, its job is just to be a taxi service. Its only goal was to get our packet to the next device in line, the one that can think globally. So as soon as the packet arrives at this gateway, that outer layer, that Ethernet frame, the little sticky note, it gets stripped away. And that reveals the IP packet inside, now ready for its real long-haul trip. And what is that gateway? It's your router. Now, a router is totally different from a switch. It couldn't care less about those local MAC addresses. The router's job is to be the big highway interchange for the entire internet. It looks at the global destination IP address on the packet, and its whole job is to figure out which highway to send it down to get it just one step closer to where it's ultimately going.
So how does it make that decision? How does it pick the right highway? Well, it looks at its own personal decision map, which is called a routing table. And here's the really cool part. The router doesn't know the entire path from start to finish. It's not like Google Maps. All it knows is the very next hop. It looks at the packet's final destination IP, finds a matching network in its table, like say, oh, to get to the 172.16.2.0 network, and the table tells it, okay, for that you need to send the packet to the next router over at 172.16.4.2. Then, it wraps the packet up in a new local frame and sends it on its way to that very next stop.
And with that, our packet is officially out on the open internet. It's hopping from router to router, city to city, maybe even continent to continent. But for this whole thing to work, with literally billions of devices all trying to do this at the same time, the system needs a few very clever tricks up its sleeve, especially when it comes to addresses.
And one of the biggest tricks is something called Network Address Translation, or NAT. The best way to get your head around NAT is to think of your router as a company's receptionist. Inside the company, right, everyone has their own personal phone extension, maybe just 4 digits. Those are like your private internal IP addresses at home. But to the outside world, the entire company just has one main phone number. That's your single public IP address. NAT is that receptionist. It's the one who keeps track of all the internal calls and connects them to that one main number, which lets all your devices, your phone, your laptop, your TV, share one single public address.
So why do we even need a clever trick like NAT? Well, it's because the Internet's original addressing system, IPv4, only had about 4.3 billion addresses available. And that sounds like a lot, but with the absolute explosion of connected devices, we actually ran out of them years ago. Now it was basically this brilliant workaround, this patch that let us stretch the life of IPv4 by allowing entire private networks to hide behind just one of those precious public IP addresses. But the real long-term solution is something called IPv6. This is the new standard. And instead of the 32 bits that IPv4 used for an address, IPv6 uses 128 bits. The result is, well, it's a number of addresses so big it's almost impossible to wrap your head around. We are talking trillions upon trillions, more than enough for every single grain of sand on Earth to have its own IP address. It's enough for every phone, every car, every toaster, every light bulb to have its own unique public address forever.
So, after all that, hopping across who knows how many routers, our packet finally arrives at the server it was looking for. It made it. But the journey is only half over. The server gets the request, and it does the whole process in reverse. It unwraps each one of those layers to read the data inside. Then, it grabs the web page you asked for, and it does the exact same thing we just talked about. It wraps that web page data in all the same layers, TCP, IP, Ethernet, and sends it on the return chip all the way back to your computer's IP address. And when it finally gets back to you, your computer unpacks it all, and bam, the web page appears on your screen. And think about this, that entire round trip, with all of its layers, all those addresses, all those decisions, it happened faster than you can blink, in milliseconds. It's just an incredible testament to how robust and scalable this system is. So the next time you click a link, maybe you'll appreciate that incredible little journey. And it leaves us with a final thought. What happens to our world when it's not just our computers making this trip, but billions more devices, your car, your fridge, your toaster, making that same journey every single second of every day? Because that is the future the internet is being built for right now.